Hi everyone, my name is Sean Sinclair and I am a second-year PhD student at Cornell University in the Operations Research Department. I'll be talking briefly on our work on adaptive discretization for model-based reinforcement learning. First off, I'll start by summarizing the main contributions of our algorithm. First, we were able to develop an efficient model-based algorithm for large state action spaces that are endowed with a metric. Throughout the process, we use a new proof technique for transition kernel concentration, which avoids needing to use a covering argument over the space of value functions. And lastly, we show that our algorithm achieves sublinear dependence on the three main components of time complexity, storage requirements, and also regret. To start off, I want to briefly summarize the problem setup that we consider. We consider the episodic reinforcement learning setting, where every step can have a different reward function and transition kernel. As we're working in a metric space, we need to impose additional assumptions to make the problem tractable, and so we assume a non-parametric Lipschitz assumptions on the reward function and the transitions with respect to the Wasserstein metric and the metric that we have on the state and action space. And as always, our goal is to try and minimize the regret, which is the added difference in the value function for the policy that the agent uses versus the value function for the optimal policy. As we're considering model-based reinforcement learning, it's important to first start up with a warm-up of the tabular or the discrete setting. In the offline setting, under the setting where you know what the reward function and the dynamics are, the optimal policy can easily be found by solving the Bellman equations, which relates the quality function for one step in terms of the reward function, the transition function, and the value function for the next step. It also gives you this nice format for the optimal policy, being greedy with respect to this quality function. In the online setting, still in the discrete tabular setting, most algorithms simply maintain estimates for the unknown rewards and transitions and just replace these quantities in the Bellman equations. And so now you have estimate of the quality function is estimated reward plus estimated expectation of the estimated value function, where you add on a bonus term that ensures that everything is optimistic. And so this makes sense in the tabular or the discrete setting, where you can keep track of a finite number of estimates for the rewards and the transitions. However, if you're working in a continuous setting, the domain for the rewards is the entire state and action space. And this motivates using a discretization approach because it makes this entire process more tractable in a continuous setting. And so what our algorithm does is it maintains an adaptive partition of the state and action space. And what an adaptive partition is simply a subdivision of the entire state and action space into different regions that have different sizes. And so we maintain a partition of the state and action space, and we also have to maintain the induced state partition, which is found by taking the partition of the state action space and projecting it down into the state space. This is needed because the domain of the transition kernel is the state and action space, and the range is the state space. And so we keep discretizations of both of them in order to make sure that these computations are more tractable. With the discretizations in place, we keep estimates of the rewards and the transitions across the entire state and action space. And once we have these estimated rewards and transitions, we plug them back into the Bellman equations, and we use full or one-step planning in order to determine estimates for the quality and the value function and also the optimal policy. Where now the quality function is defined over these partitions of the state action space, the value function is defined over the induced state partition, and again, in the Bellman equations, we have estimate of the quality is estimated reward plus estimated expectation of the estimated value for the next step with a bonus term. And again, the optimal policy is the one that's greedy with respect to the estimate of the quality function. This is nice because it allows the algorithm to be more tractable by keeping track of a fixed and finite discretization of the space. The major contribution of the paper and also the algorithm is deciding how to maintain estimates of the transition kernel. And so what we do is we estimate the transition function over a uniform discretization of the state space up to the precision of the ball. And so here we have a ball on the left-hand side whose diameter is roughly a quarter. And so we maintain empirical estimates of the transition kernel on a quarter discretization of the state space. What this does is kind of twofold. First, it ensures that the accuracy of the estimate is proportional to the diameter, which typically you need for these adaptive discretization algorithms. And the second point is that it limits the storage complexity for the estimates. Typical model-based algorithms have to keep track of the entire sample path that's considered throughout the process of learning. Whereas these estimates of the transition kernel are somehow figuring out the smallest sufficient statistic that limits the storage complexity of the estimate while still ensuring that it's sufficiently accurate. The last kind of idea for the algorithm is deciding when you want to subpartition a region. And so similar to the case for the model-free algorithm, we subpartition a region when the confidence radius is smaller than its bias. And what that corresponds to is splitting a region once the number of times we've been in that specific region is larger than 1 over the diameter of the region raised to the power of the dimension of the state space. As usual, new regions have half of the diameter of the parent, and you inherit all of your estimates. And what's interesting in this case is that the splitting threshold explicitly depends on the dimension of the state space, and that's different from the model-free case. And it arises as a form of bias variance trade-off, where the confidence radius, the dominating term, arises from the transition kernel, whose complexity explicitly depends on the dimension of the state space. Once we have the splitting threshold, we're able to show a regret bound for our algorithm that scales like this. So it scales linearly with respect to the Lipschitz constant that we assumed on the problem. It scales roughly h squared with respect to the number of steps, and then exponential with respect to the covering dimension for the number of steps. What we see is that we have better dependence on the number of steps than model-free algorithms. That kind of makes sense because even in the discrete case, we see that model-based algorithms have better dependence on the number of steps than model-free. What's probably more interesting is that we have a worse dependence on the covering dimension of the space. And this is because in a model-based algorithm, you're maintaining estimates of the transition kernel, and their complexity depends explicitly on the dimension of the state space. And so that's why we're seeing extra terms in the regret bound that scale with respect to the dimension of the state space. This is kind of a contrasting story to the tabular case, where we see that model-based algorithms have better regret and also empirical performance than model-free ones. For the proof sketch, you can divide it into 3 main sections. The first section is concentration and clean events. The second is a regret decomposition, and the third is bounds on the sides of the partition and bonus terms. Probably the 2 most interesting ones are the first and the third. In the concentration section, in order to show concentration of the transition kernel, we use new work on Wasserstein concentration that allows us to avoid a covering argument over the space of value functions. In the third section, we use LP duality and the partitioning rule that we discussed earlier in order to generate bounds on the size of the partition and also the bonus terms. Lastly, we do several numerical experiments showing the algorithm in practice. And I like to think of this as reinforcement learning for operations research, which is something that I like to talk about a lot. So we have an example here for the oil discovery problem. In this problem, an agent is surveying a 1-dimensional map in search of hidden oil deposits. So on the bottom, we have a 1-dimensional map and a not so hidden oil deposit as well. The agent then surveys this map, paying a transportation cost proportional to the distance moved. Surveying the land produces noisy estimates of the true value, and the transitions are perturbed by uneven rain. And what's nice about this problem is typically in reinforcement learning simulations, you'll see a lot of the simulations being focused on game playing. And while this shows that reinforcement learning is very strong and is very good at learning high complexity problems, by applying it to operations tasks, we're able to see how reinforcement learning is better able to adapt to the intrinsic complexity of the problems. And so in this problem, you can simplify it down to a contextual bandit by simplifying the transitions, or you can increase the complexity by allowing there to be more exogenous randomness in the system. With the simulations, we compare 4 different algorithms: an adaptive discretization version of a model-based and a model-free algorithm, and the same 2 algorithms done with uniform discretization. We have 4 different plots. In the plot in the top left, we have a comparison of the observed rewards for the 4 different algorithms. When you compare the uniform discretization algorithms, the ones that are model-based in green and the model-free in red, we see that the model-based algorithm has much better empirical performance with respect to the model-free algorithm. This again matches our intuition from the discrete case, where empirically in the tabular setting, model-based algorithms have better performance than that of model-free. Then, if you go to the plot on the top right, we have a comparison of the size of the partition. Again, what we see in this situation is a similar story to what we have for any adaptive discretization algorithm, that the actual size of the partition that is produced is much smaller than the one that you require when you're using a uniform discretization. Probably most interesting, though, is the plots on the bottom. These are the actual discretizations that are produced by the model-free algorithm on the left and the model-based algorithm on the right. The underlying contours of the function is the actual Q star values for the problem that we're considering, where green corresponds to a high Q star value and red corresponds to a low one. What we see in the plot for the model-free algorithm is that the algorithm has a discretization that exactly matches the contours of the underlying quality function. The similar story is there for the model-based algorithm, but we don't see the same exact matching of the contours that we see in the model-free algorithm. And this is probably due to the splitting rule in the model-based algorithms, because in the model-based algorithms, the splitting exactly depends on the dimension of the state space, where the model-free algorithm does not have any dependence with respect to that. And this creates a lot of interesting questions for future work. In order to develop these model-based algorithms more, we need to decide what is the complexity in estimating the transitions for continuous problems. A lot of the research that is typically done in these continuous settings uses a very much worst case dependence result, which obviously needs to scale with respect to the dimension of the state space. But really, we only care about estimating the transition kernel for the places where the optimal policy visits. And so understanding this dependence will be important in order to improve the regret bounds for the model-based algorithms. The other question is, what is even the correct notion of complexity for continuous reinforcement learning? Is GAP even the right answer? And so thank you so much for watching this presentation. I've included the link to the archive for the adaptive discretization for model-based reinforcement learning at the top, and then also the link to the adaptive discretization for model-free on the bottom, and a link to a longer presentation. Thank you so much.